Hello and welcome back for another VMK in the math series. In this video, I'm going to go over the dot product. When working with vectors, it's helpful to use the dot product for a number of different reasons, so I'm going to show you sort of the highlights in this video. If you find my videos helpful and you can support my website, you can do so by clicking on the store button or the membership button and purchasing some items from my website, or you can also help out just by clicking on any of the Google ads found on the side or on the PayPal donate button located right here. To start off, if we had a right angle triangle like this one right here, where this angle here would be a right angle, we can get a relationship between each of the sides of this triangle by using the Pythagorean theorem. Let me label this one side here x, this other side here y, and this third side here r. With those three sides labeled, we know that the magnitude of r squared is equal to the magnitude of x squared plus the magnitude of y squared. This is basically the Pythagorean theorem. We also have another relationship between the sides of the triangle and one of the angles. If we choose this angle here to work with, then we can write the following formula. The cosine of that angle, cos of the angle, is equal to the magnitude of x divided by the magnitude of r. Another trigonometric relationship is the sine of that angle. If we have the sine, that would equal to the magnitude of y divided by the magnitude of r. So these formulas, just make sure that you understand them because we will be coming back to them in a little bit once I start talking about the dot product. Okay, the dot product of a vector is defined as following. Actually, let me draw two vectors here. We'll have one vector here and another vector here. I'll call this vector A and this vector here B. The dot product of A dot B is equal to AX times BX plus AY times BY plus AZ times BZ. So in other words, what we do is we take the individual components of the vector A and multiply them with the individual components of vector B. Once we multiply them together, we just add all the individual components and the result is a scalar value. So this is going to equal some number here. It's no longer a vector, it's just a regular number when we apply the dot product between two vectors. Another way to write the dot product between two vectors is the following. A dot B is also equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So if this is the angle here between these two vectors, then if we know the length of vector A and the length of vector B, and we multiply everything here together, we can get the dot product as well. This relationship of the dot product is more useful when you want to calculate the angle between two vectors. So this angle here. A lot of the times you will know what these two vectors are, but you want to know the separation angle between these two vectors. So using this, you can rewrite the formula to be something like so. A dot B divided by magnitude of A times magnitude of B is equal to cosine of the angle. And then if we just take the arc cos of both sides, we can get the angle. So theta is equal to cos inverse of this quantity here. I'm just running out of room, so I'm not going to rewrite it. Okay, now let's take a look at some interesting facts about the dot product. If you were to dot one vector with itself, what would you get? Well, we could apply either of these formulas to see the result, but let's work with this one because the result is actually more clear. If we take A dot A, we'll get the magnitude of A times the magnitude of A times the cosine between A and A. Well, because A and A are the same vector, the cosine of the angle is going to give you 1. The angle between the two vectors is 0, so cos of 0 is equal to 1. So this cancels out, and you're left with A dot A is equal to the magnitude of the vector squared. Like so. This is a useful relationship which we're going to come back to again, but also remember this when trying to calculate the length of a vector. If you need to know the length of A, you can quickly calculate A dot A and you'd get the square of the length. If you truly are interested in the length, you could just square root the A dot A and you'd get the length of a vector. It's a quick way to calculate the length of a vector. One of the most useful things to do with the dot product is to find projections of one vector on top of another vector. So for instance, let's say you had two vectors as shown here. Let's call this vector here v, and let's call this vector here u. If I wanted to know how far this vector here projects onto u, that would be something like so. If I just take this vector and project it straight down on here, imagine as if there's like a sun over here and it's shining a shadow of this vector on top of this vector here. So the v vector would cast a shadow that would lay down on top of the u vector all the way up to this point here. What we want to find is what is the length of this vector right here. Well, before we approach this problem, let's go back into our previous Pythagorean theorem and take a look at what we have here. The projection problem is very similar to the Pythagorean theorem. If we look at the hypotenuse of the triangle here, and we'll call this the vector, the first vector, then we can see that the projection of r onto x is this right here. So if we had a longer vector here all the way out to here, we could say that the projection of r onto this horizontal plane is equal to x, which we can calculate using these formulas here. The magnitude of x is equal to the magnitude of r times cosine of our angle. The general case of our problem is a little bit more difficult because the vector that we're projecting onto is not perfectly horizontal. As you see here, it's actually a vector on its own in 3D space. So how do we take care of this case? Well, let's start off with the dot product. We know that v dot u is equal to the magnitude of v times the magnitude of u times the cosine of our angle. If we look at our triangle closely, we can see we have a Pythagorean theorem relationship built into here. V dot u divided by the magnitude of u is equal to the magnitude of v times the cosine of the angle. Well, this here should look familiar to you. Magnitude of v times cosine of the angle is actually equal to the magnitude of this green vector here. So let me label that. I'll just call this A, and A on our diagram here is the distance from this point all the way down to here. Well, what we are interested in is not just the distance, but rather the vector. The vector has this magnitude, but it also needs a direction. And the direction will come from this vector u. U itself goes from this point here all the way down to this very end. Well, we want to know the unit vector of u, and we can always get the unit vector by taking the vector itself and dividing it by its own magnitude. This will give us the unit vector of u. If we take the unit vector, multiply it by a, that gives us our result. This will give us the projection of v onto u. And we can actually simplify the formula a little bit. So the projection is equal to v dot u divided by magnitude of u times u hat. U hat is equal to u divided by magnitude of u, so that will give us v dot u divided by the magnitude of u squared times the vector u. And as we saw earlier, the magnitude of u squared is actually the dot product of u by itself. So v dot u divided by u dot u times u itself is equal to the projection that we're looking for. So using this formula, you can now find the projection of any vector on top of any other vector, and it doesn't matter its orientation. U could be pointing in one direction, v could be pointing into another direction, and you still get the proper projection value. So for instance, let's say we had something like this. If we had one vector pointing this way, and we had, and we'll call this v, and we had another vector pointing this way, we'll call this u, then if you apply the projection formula, you're going to get this vector here. You'd get the vector from the start here all the way down to the end. U itself will behave as if it's a flat plane, and v will be projected right onto it. This is helpful whenever you're programming things like shadows, or you're trying to calculate distances based on vector math. The vector projections work both in 2D, 3D, so it doesn't matter how many dimensions you have. The projection formulas work perfectly well. Just remember your basic formulas for the dot product, A dot B, where you have each individual component multiplied together, or the other dot product formula where you have the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between the two vectors. I hope this tutorial was helpful, and if you have any specific math questions, feel free to email them to me and I'll create a video for you.